This is the 2022 Higher Year 10 Physics exam. So there's your formula sheet, and on to the first question, which is circuits. So for 2 marks, we're going to add a variable resistor and a voltmeter. Make sure your V is capital, and it's quite clear. Mine's not there, I just realised. But try and be as clear as you can. Here's our graph then of voltage against current, and clearly this is a lamp because of the shape of the graph. Then we're asked to compare some data to see if when the current doubles, the voltage triples. So I'm going to use sets of data from the graph. So when current is 0.5, the voltage is 0.9. I got that from the graph. When current is 1, then the voltage is 2.4. And then what I've done is divided these values into, so if I'm doubling current, I'm going to divide 0.9 into 2.4 to see if it triples. Well, it doesn't. It's 2.6 times as big. And then I'm going to do the same. I'm going to double from 1 to 2. And I'm going to see how many times 2.4 goes into 8.4. And it's actually more than triple. So it's not triple, so I'm going to disagree. Those values there I got from the graph by looking at particular points when the current was 0.5, 1 and 2. Okay, so we're going to calculate the power when the maximum power. So we need maximum voltage. So the maximum voltage from the graph is 12. And when the voltage is 12, the current is 2.25 on the graph. So I'm just going to use that equation to give me 27 watts. Nice easy one here then. It says now that we're using a fixed resistor. Repeated with resistor. When the voltage is 12, the resistance is 6. So I'm literally just putting my values in there to give me 2. That's my new current. So I'm going to draw a line for that on the grid. Because it's a fixed resistor, it's going to be a straight line. So my current value is going to be 2. And that's going to go back to the origin. Remember now, my voltage is going to be maximum 12 and then 2 there. So you just bring a line all the way back to the origin with that one. We've got a sealed box. We want to find out if a diode's inside. Well, there's a way that we can do that. We need to connect it in series. And if the bulb lights up, then we've got lucky and the diode is facing the right way. Remember, diode will only allow current to flow in one direction. So you might get it not lighting up straight away, or it might light up. Also check the ammeter readings. If the ammeter reading's high, and then when you reverse either the cell or the sealed box, you actually turn it round the other way. Then if you stop getting a lit lamp then, or if there's not reading on the ammeter, then you've got a diode. If you've got the same both ways, then it's not a diode. It's going to be something else. And then that's what the shape of the graph's going to look like. So it won't allow much current at first, but then as the voltage goes up, it's going to allow a lot of current. And it kind of, to me, that looks like the shape of a D. Okay? If you put a little, in fact, I'll do it there. Got the shape of a D now. For diode. Question 2. A lot of work for question 1 there. It was quite a long question there. It took me 3.5 minutes to do that one. So microwaves now. So on to waves. Well, I've got 2 waves there, and it's 12 centimeters. So one wave is going to be 6 centimeters. Bear in mind now that's centimeters because that caught me right out by here. You can see I didn't do the conversion. To get it into frequency, it's got to be converted to meters. So when I get my wave speed now, which is the speed of light, 3 times 10 to the power 8, and my wavelength, and I'm finding out my frequency. So I'm just going to remember to get marks, just put it in the formula as you see it, and then you can rearrange to get 5 times 10 to the power 9 hertz. This is your standard wavefront diagram. So that's all you're doing is getting your ruler perpendicular to this, so at right angles, and then you're just going to follow these lines off. Because we're moving to a less dense medium here, the wavefronts are going to be bigger, but you can't get it wrong so long as you're working off these. Geostationary satellite then, it's a satellite that orbits the same time as the Earth, and it stays above the position because it's above the equator. So we can say the satellite orbits in the same time, 24 hours, that it takes the Earth to spin once, and that's why it stays the same position. Geosynchronous will be going around the Earth a different way, not around the equator, and it syncs up every 24 hours. Last part of this question then, we've got a bunch of satellites. We're sending a signal from 1 to there, and then back from there to 2. So it says unit equation. So what we've got then, yes, so we've got it. Let's just have a look here. Yeah, this is an awkward one. I tell you what I haven't done is I haven't drawn it on. So let me get my pencil. So the signal is going, actually draw this on. I'll draw it on in red. Oh no, my pen stopped working. So I'm going to have to freehand this. So it's going up here. Oh, let's choose another color. It's going up, and then it's coming back down to that little station, and then it's going to go up from that station up to that satellite, and then back down. So it's actually, sorry, let me draw that again. It's actually going 4 times up and down. Well, because it's going 4 times and it's got a distance of 3.6 above the Earth, we need to times that by 4 to give us that distance. So now that we've got our distance, and speed equals distance over time, we can rearrange for time once we've filled in our blanks. So it takes 0.48. Now, obviously, there's a couple of ways you could do that. You could just do it to the distance and then times by 4 at the end. But that's just one way I've done it. It says that it suggests a signal being sent in the opposite direction. Okay, so it would be quicker. No, because it's the same distance traveled, and I have to do it 4 times as well. So I disagree with that. Question 3 then, initially looks like a 6 marker, doesn't it? But it is a 6 marker. It's just, this is a really nice question, actually. You've got to explain what the live wire is, the neutral wire, and the earth wire. So they're just definitions, okay? So I'm not going to go through that. And then what's an MCB and an RCCB? The big difference with these two is that this protects the circuit or the appliance, and it prevents overheating, whereas this protects the user. This is a lot more sensitive because it detects that difference in the current between your neutral and live wires, which is why we've got this live wire and neutral wire there. Now we come on to the 6 marker, which is a solar panel. So initially, there's a lot to get your head around, but really what the question's asking for is conduction in a solid, and not just a solid, in a copper piping. So it's going to be a metal, so it's going to include free electrons. So we've got particles vibrating faster and colliding with their partners, their neighboring particles, passing on that kinetic energy, that movement energy, and then the free electrons are even going to pass more energy through that material. What's convection then? There's a lot of definitions actually going on here, isn't there? Convection is going to be the heated liquid is going to rise, or fluid we could say, because it becomes less dense, so it moves on up. Then we've got a little numeracy question. So we've got each square meter is that. So we've got 2 square meters there. So 2 times 960 is going to be that, 1920. And then we want a third of that. So a third is just, if you type that into your calculator, you're going to get a third times 1920. And that's going to be 640. Coming on to question 5 then. This is your 6 marker, isn't it? Did I just say the other one was 6 marker? There's a lot of wordiness. Yeah, this is your 6 marker then. This is describing how we generate power, how it's efficient, and then the national grid. Yeah, so how it's become safe then. So first of all, let's talk about the generation. The generation, so gas is burned to produce steam, which turns a turbine, which is connected to a generator, which produces electricity when you rotate it. How can we get it efficient then? Well, the power that comes directly from the power station, we're going to connect it to a step-up transformer, which is going to increase the voltage. If you increase the voltage, the current needs to decrease. And this means less energy lost as heat over the overhead cables. How do we get it safe for consumers then? We're going to use a step-down transformer now to step it, so it's going to increase the current now and reduce the voltage to make it safer for users. Coming on to the last question. It's actually quite a quick paper, isn't it? Lots going on in this question. So not only here, but down the bottom as well. So a farmer uses this much and it costs that much, but now he's decided to improve his efficiency by spending this much out, which has reduced it to that. So we want the reduction in units, which is going to be 12,000 kilowatts. And then let's times that by the cost. So he's actually saving 2,400 pounds, 2,400. What's the payback time on that then? Cost over saving. This one is not given to you in your front sheets. So you need to get the cost that it cost him, 152,400. Put it over the savings to get you 63.5, or round that up to 64 months. Never round down, always round up when it comes to payback time. OMG, look at how much is going on. We've got 150 cows, each 200 kilograms, and they collect 60 kilograms. We've got 0.05 gas. We've got a generator, total of 5.3, and then the useful there is 1.9. Okay, so let's see where the questions go in. Calculate the efficiency of methane gas. So we're going to look at these two by here, first of all. So percentage efficiency is equal to useful over total times 100. So I got my useful, which is 1.9. I got my total, which is 5.3. No conversions needed because they're all in kilowatt hours. So just be careful of the conversions. Since it is a last question as well, they might try and catch you up there. Or, you know, something like a megawatt hour. So you just have to be very careful. In this case, it's the same, so it's 35.8%. I should have maybe stuck a percentage on the end there. Okay, so 5 marks. Lot to do here. So the farmer thinks that he's going to be producing this amount of energy. We need to prove if he is. So it says 1 year equals 52 weeks. First thing I need to do is to find out the weekly mass of dung. So the way I do that, I go back and I see, I think he had 150 cows. And they collect 60 kilograms. So let's work that out first. So I'm going to collect 9,000 kilograms per week. And now that is per week, and I realize that there's 52 weeks in a year, but I'm going to do that as my last step. I'm just going to keep going now. If I've got 9,000 grams of dung, how much gas is that going to release? I think it told me it was 0.05 there. So it produces this much gas. So now I want to times it by that. And I'm going to get 450 meters cubed. That's my volume of gas. Now, I know my volumes of gas. I can convert to kilowatt hours because it tells me that as well. So the kilowatt hours is going to be that, 1.9, the useful energy, which is there. And that gives me 855 kilowatts, and that's per week. So now to get into a year, I simply times that by 52, and it gives me this number, 44,460 kilowatt hours, which is not that. So the farmer is incorrect. Last question then, we're told that carbon dioxide is a lot better than methane gas because it's 30 times more effective at trapping heat, which is going to contribute towards global warming more. So explain whether collecting cow dung to using biogenerators benefits efforts to reduce human impact on greenhouse effect. Well, if it's going to reduce the amount of methane added to the atmosphere, and since carbon dioxide is less harmful, it is better to burn the methane. And that's the end of the paper. So as always, if you've got any questions about anything we've just sort of spoken about, see your teacher, and hopefully this video has been very helpful to you.